Hello everyone. Welcome again on my YouTube channel. Today I'm going to be presenting a project I did in Course Unity Computer Vision at Makerere University. Currently, I'm pursuing Masters in Computer Science. So the project is titled Garden Monitoring Using Computer Vision and Machine Learning. And some of the techniques I used are feature extraction, classification, and deep learning approach. Is my registration number and my student number. Without wasting time, we can start. This is the presentation outline I'll be following. And to start with the introduction, for this specific project, I considered three crops, which are cassava, maize, and sugarcane. But as we know, in every garden or field, you can never find only crops. You have to find also grass, other ground. So I also added the fourth class, which is grass. The importance of plant or crop classifications, we know that these crops plays a crucial role in food security and income generation. And furthermore, to come up with these sort of classifications can really be helpful or is essential to the community in general. To come up with these models, we know that the traditional models really complex because they really depend on taxonomic expertise of people who really understand the crops and additionally manual data collection, which can be hectic because you really need a lot of data to do these sort of models. On top of the data, again, you really need experts who know which kind of crops. Okay, as human being and according to your age, you can really differentiate the crops, but sometimes it's very hard accordingly. And then it does really tends to two main problems. One, the interpretations, and another one, efficiencies. Computer vision and machine learning came as a rescue for these kinds of challenges because they really provide an alternative ways of doing this or alternative ways of avoiding these kinds of limitations. So after getting the images, what we do feature extractions from these images. So for my project, I used three approaches. One is Swift, another one is ORB, and then the third one is color extraction, but there are very other more like soft and so on. And then after extracting features, I used k-means to represent 100 features, 10 best 100 features, and then after that I used PCA to sort of select 10 best features from the features, and then I was able to train my models. So here I trained two types of models. One is the classical ML model, which is k-nearest neighbor, and then the second one is the deep learning models. Here I trained also two, which is a simple CNN model, and then a transfer learning model, which I used MobileNet as a base model. So the importance of these models, we really know that if you train a very nice model, it can help in agriculture, for example, in disease detection, the classification itself, the yield estimation, automated monitoring system, and so on. So you need a very nice data set to do this, and you need to train as many models as possible for you to be able to compare the models and be able to evaluate which one is the best, which one works better accordingly. So some of the related work from what I've been reading, previous studies do tend to focus the most in disease detection. One of the paper I've recently read is the one around cassava, which was a cassava mosaic disease detector. But we have some other literature related to that. One is the Bezo and his friend. They were able to combine feature extracted by VGG19 with the features they extracted themselves using Swift, and they were able to really do a very impressive model, a random forest classifier with a 93% accuracy. Another paper was the one done by Salvador with his friends. They employed a pixel-based classification approach using SVM and random forest. They were able to get a 97% accuracy. And then another one is Nisha. So for them, they deployed an image recognition system for cassava leaf diseases. So with this and many other modes, we can see that they do demonstrate the potential of image feature extraction and machine learning models in crop classification and detection. But what we can see that there is a need of further research to develop or to improve robust and accurate models for improved agriculture practices and crop management, especially in the classification area. So to sort of approach that, my solution did two ways. One was developing a model using a classical ML, which is K-nearest neighbor. So what I did for this approach, I extracted images from the video we were shared by our lecturer, and then I was able to extract frame using VLC, and then from those frames, I was able to crop them and then get specific images I intended to use. And then I used same data preparation method for all my models, including the CNN models, the deep learning models, and the classical models, for the target to sort of be able to compare the same data. So here, for example, I was using 256 resizing window for all the images. And then after data preparation, I used feature extraction, which I used 3 types: Swift, ORB, and color histogram. And then after feature extraction, I used a bag of words to select 100. I mean to group 100 features, and then I selected from those 100, I selected 10 best features using PCA, and then I trained my KNN model. So for the second approach, after data preparation, I just went to CNN and transfer learning model. That's it, without feature extraction, because the CNN model does that, and the transfer learning model sort of use the features from the model that you're going to use as a base model. So this is the data set. This is how it looks like. You can see we have some cassava on top left, cassava, maize, sugarcane, and some grasses. And the images I was able to crop in total 370 cassava, 17 cassava, 304 maize, sugarcane 114, and 287 images. They are not balanced, but still they were able to produce a very, very nice models. And again, something to remind, I did not use any augmentation technique here. I just used the data the way they are. So this is what you get after using Swift. These are feature points. So what we know that Swift is just scale variant feature transform algorithm that extracts features from the images. So here you get key points based on the local intensity extreme in the different scales of the images. And then for ORB, it's similar. It's similar as Swift, but ORB used 2 techniques. One is FAST, which is feature for accelerated segment test, and then the second one is BRIEF, which is binary robust independent element features. So it's sort of the same, but for ORB it uses those 2 techniques. So these are the results I got. So after extracting the features and select the features, 10 based, I divided my dataset into 2 parts, 715 images for training, or 307 images for testing. And then for this model, I was able to get a 92% on the model trained using Swift features. So you can see the model only misclassified 27 images. It was a very nice model. For ORB, still similar data preparation and splitting of the data, but for this, it performed slightly less better than the one using Swift features. So here it got an 80% accuracy on the test images. And then from the confusion matrix here, now you can see it misclassified 54 images, kind of like twice the images that were misclassified in image trend using Swift features. So, but again, it wasn't that much bad. All right. So, for the color histogram, it did not perform well. One, because the color histogram has their own specific way of feature extractions. But the way I approached this, I wanted to sort of do the same thing. Select, do the bag of words, do the same PCA, same method to Swift and ORB to sort of mimic the same thing. So it tends to not perform very well. It got 50% accuracy on the test set. Sort of, you can see from the confusion matrix, it was more or less guessing the images, if I can call so, except from the class 2, which is maze. So for the summary, we've seen that the KNN model developed using Swift did perform very well, which is 92%, followed by the one with ORB with an 80, and then lastly the color histogram. So for the second approach, for deep learning model, I trained two. One is CNN model. For the CNN model, I used a very simple one with couple of convolution layer followed by max pooling layers, and then flattening those features, and then after that, be able to pass through that to a dense layer. And then here I was using Adam optimizer, a learning rate of 0.0001, and then across the entropy rows with an early stopping to avoid overfitting. So this is how the model performed. It also performed nicely. You can see the loss curve and the accuracy curve really performed better. But we can, okay, let me go. We can see for that model, it got 96% on the test set, with only mix classifying 10 images from 103 image for the test set, and the loss of 0.1 range between the test loss and the trend loss, which wasn't that very bad. So another one was a transfer learning model. I trained that using a MobileNet as a base model, loading their weights and use that as a backbone. So for this one, why MobileNet? MobileNet because it's lighter and it can be imported into the mobile phones, and then farmers can then use them to classify using in their garden. So this is a very light model. You can see how I trained so many epochs, but the model was still beyond 10 MBs heavy. So it was really a very light model, while I have even trained it that much high. So you can see the model performed also nice with nice curves for the losses and trend. And it got an 83% on the test set with a loss differences of 0.03. So this also performed better. But it misclassified 11 images, which wasn't also bad. So for the conclusion, I was able to get the images, extract them, crop them, then do the feature extraction, use bag of words to select, and then select using PCA nice features, and then train KNN and deep learning models. The beta model was a deep learning model. And that model can be improved by using augmentation, or even get better, or even get more data. Thank you so much. These are my references, and thank you so much.